So we return again to the image processing sequence, and this time we're up to the image pre-processing step. And we're going to consider here both geometric and radiometric correction. So first of all, why do we need to perform image corrections, and what is actually involved in pre-processing? The most important thing here is that we need to provide a data set that can be used to extract spatial information. And in this case, we require digital image data that are first of all in an accessible file format and with the relevant and accurate metadata, that have been corrected for all geometric distortions and also registered to an accepted vertical and horizontal datum. We need to make sure that there's an appropriate map projection, so really considering whether we want to preserve areas, distances or shapes, and that there's also a spatial coordinate system. And these things allow us to integrate them with other spatial data sets in a GIS. We also need to ensure that the data are free from any systematic radiometric distortions, so any brightness variations throughout the images. And we'd often like to be able to convert the digital numbers retrieved by the satellite to physical units of electromagnetic radiation, such as radiance or reflectance. And we also need to be able to remove atmospheric attenuation, so we're ensuring that we're getting the true signal rather than the signal from the atmosphere. Once we've done all these, we can use them in an image processing system or GIS to produce spatial information products. And it's important to note that multi-day analysis can only be performed on geometrically and radiometrically corrected data. So let's have a look at a couple of pre-processing steps. If you look at these image examples on the right-hand side, this is from near Wellington in New Zealand. If you look at the upper image, for example, you should be able to see that you can tell that it's a hilly environment. And obviously here it's a standard false color composite where the vegetation appears red. And in this case, I'm actually looking at landslides. But the important thing here is that the data have been processed to remove the effects of the terrain. So our ability to actually tell that it's a hilly environment here is because we can see both sunlit and shaded slopes. But what this means for remote sensing is that if we were to create an image classification based on the upper image, we would classify the sunlit slopes differently to the shaded slopes because the vegetation actually appears different. It appears darker on the western face of those hills. Now if we look at the lower image, it actually appears that that elevation has been taken out. And it's not so good to understand contextually information about the image, but it's much better for obtaining spectral profiles, for example. So really with pre-processing, we need to correct distortions that have been introduced in some way during image acquisition. So these involve geometric corrections or related to spatial corrections, which really give us information about where the image has been acquired and will remove anything like roll pitch or yaw distortions from an airborne camera system, for example. Radiometric and atmospheric corrections, on the other hand, is really considering the conversion of digital numbers or the values obtained by the satellite to at-sensor radiance or reflectance units. This also involves correction of atmospheric attenuation, and this will give us a more pure signal without considering what the atmosphere is contributing then. It may also consider things like the interface correction, so if we're working with an air-sea interface, air-soil, etc. And other corrections that we might make include topographic corrections like the images on the example on the right hand side, and images to correct for sun glint at the water surface, for example. The output of pre-processing will give us non-distorted image data with coordinates, projection and datum. So here's a couple of examples here, and again this is using the imagery from Heron Reef, and the top example we've seen a couple times now before. This is having a look at a form of geometric correction. So we've really removed the roll pitch and yaw to give us a geometrically correct image, and this also has coordinates associated with it, so we could make measurements of distance and area, for example. Now the bottom example is an example of removing sun glint from the water's surface. So if you have a look in the left-hand image, you'll be able to see that there's quite a bit of glint at the surface of the water, and it's actually obscuring our ability to look into the water and see the coral. The image on the right-hand side, however, has that removed, and you can see the coral under the surface of the water a lot clearer. Part of pre-processing also may involve mosaicing a number of image strips or squares together. So again, this is the example of Heron Reef, and this is a number of image strips that were taken through the individual flight lines of the aircraft. You can see they don't line up perfectly, and there's also a bit of brightness variation between each of the image strips. So through the process of pre-processing, we've gotten rid of a lot of the distortions to come up with an image that actually looks like this, and it looks much better, and it's much better also for extracting information about the individual features. We'll talk a little bit about auto-rectification, and this is really where we get an image and combine it with a digital elevation model and ground control data from a GPS or satellite ephemeris data to give us information on exactly where the image was captured on the surface of the Earth, and to remove any geometric distortions there. So the example here is a spot scene from Wellington, and the raw data is shown on the left-hand side. This is combined with satellite data about the location of the image, a digital elevation model of the location, and then processed through MV to give an auto-rectified image. So this will be able to give us true coordinates for any location. So really what we want to be doing is to remove any systematic distortions and provide these corrections. So these are distortions that are able to be corrected from platform ephemeris data and pre-flight calibrations. Okay, so it's stuff that we know about based on what's happening with the platform at the time of image acquisition. And it might be to do with platform height, its attitude in terms of roll, pitch and yaw, and the velocity of the aircraft at that particular time. And this is all transmitted with the image data and provided in metadata files. So these distortions are corrected by using set transformation equations, and these are relatively simple. So here's an example of some aerial image distortions, and bearing in mind that some of these distortions will be different from satellite based platforms as well, because of the stability of the platform as a satellite compared with an aircraft. So I've got listed a number of different types of distortions here for your reference, but I'm not really going to go into too much detail for each of those. Non-systematic distortions and corrections are parameters that vary non-systematically. Okay, so they may vary at different points in time. So this might be to do with variations in the platform stability, and could also be to do with variations in altitude, both of the sensor and the terrain. Now, usually you purchase data and it's been processed to correct for these. Otherwise, you do it yourself. So it depends on how much money you want to spend on your data set. But many of these things we can correct for using ground control points or known locations on the Earth to actually attribute spatial information to non-spatial data sets. So here's some correction options. So for example, if I have an image that is unregistered, so it doesn't have coordinates attached to it, basically what I can do is use a topographic map sheet that has coordinates and get the software to tag similar locations. For example, I could pick a grid cell where I can also recognize a particular feature on the non-corrected satellite image and work out what coordinates based on the topographic map were associated with the unregistered image. So really what we're trying to be able to do is get down to fine detail to accurately locate a single pixel. And what we're trying to do is, when we go through this process, is to really keep an even spatial distribution over your entire image. We also want to select stable features as our control points. So bend in the river, for example, is not particularly stable because it may change over time. And it's important to understand the number of ground control points that are required. And we'll go into this more in the advanced subject of remote sensing, but really you're looking at a minimum of 6 ground control points, but the more ground control points you have, the better.